So, good evening, everyone. For today's class, we mostly discussed about the some questions related to the partition function, and in the previous class also we have discussed the similar some concept from partition function, but this tutorial we will extend our discussion. Okay, so today's topic will be tutorial 6. Tutorial 6. Okay, so so it will be mostly on partition function, and if time permits we will also discuss about discuss some problem from the current assignment tree. Okay, if time permits. Okay, so now let's start from question 1. Okay, so question number 1. The translational partition function of each atom is 8 into 10 to the power 33 at 3700 Kelvin in a volume of 0.064 meter cube. What is the thermal wavelength of the matter? Okay, so and the options are: option A 10 to the power minus 12, option B 4 into 10 to the power minus 12, option C 2 into 10 to the power minus 11, and option D 2 into 10 to the power minus 12. Okay, so this is the question. So basically you have to find out a translational partition function. Okay, translational of hydrogen atom. No, the translation partition function of hydrogen atom is given actually 8 into 10 to the power 33 at 3700 Kelvin, a volume of this 0.064 meter cube. Then what is the thermal wavelength of the matter? Okay, so basically a hydrogen atom, just a single hydrogen atom in a volume which is contained in a volume of 0.061 meter cube at 3700 Kelvin. The transition partition function value was 8 into 10 to the power 33. Then from this information we have in our hand, we have to calculate the thermal wavelength of that matter. Okay, so before solving the problem, let me just briefly discuss some concept about the thermal wavelength. Okay, so what is basically thermal wavelength? Okay, so answer. So thermal wavelength also it's known as de Broglie thermal wavelength. De Broglie wavelength. Same thing. Both are basically point towards same thing. Okay, so what does this mean? This actually measure of the quantum mechanical wave nature of particle at a given temperature. So it basically like at a temperature, so de Broglie wavelength basically gives you what is the like quantum mechanical wave nature. Okay, so every particle has a quantum mechanical wave nature, right? So uh, this, by calculating this de Broglie wavelength, you get the quantum mechanical wave behavior of that particle at a certain temperature. Okay, and it also like it's a wavelength, right? So it provides a typical wavelength. It's like a typical number. Okay, wavelength associated with a particle moving with thermal energy. Okay, so this is it. So this is basically definition of thermal wavelength. Now what is the expression? So the definition of thermal wavelength is basically lambda thermal equal to h by root under 2 pi m kBT. So this is the basically the expression of the thermal wavelength, lambda thermal. So here what is the thing? So here uh, h cut is the Planck's constant, m is the mass of the particle, kb is the Boltzmann constant, which is value you already know, 1.381 into 10 to the power minus 23 joule per Kelvin. T is the absolute temperature. Which should be in Kelvin. Okay, so this is, so let's suppose any particle which is at a thermal temperature at T Kelvin, then the wavelength, that quantum mechanical wavelength that is associated with that particle, the value of the wavelength basically associated with the quantum mechanical nature of the particle is given by this expression. Okay, this is known as the de Broglie wavelength or thermal wavelength of a particle. Okay, so uh, what does this actually means? This basically, this wavelength actually in classical, in classical sense, this wavelength basically represent the quantum mechanical spread of the particle due to its thermal motion. Okay, so what is that quantum mechanical spread? The spread is like captured by this wavelength of the particle at a certain temperature T. Okay, and what is the physical? The physical meaning is that the thermal wavelength basically characterize the scale at which quantum effect become important. So if the, so what happens why we need this lambda thermal? The reason is uh, this lambda thermal basically, this lambda thermal basically, so this lambda thermal basically what gives us, this lambda thermal is the gives us the scale at which quantum effects become important. Okay, so what does that means? uh, so if suppose there are many particles, okay, and the lambda thermal associated with a particle is larger than, if lambda thermal is larger or equal to the interparticle distance r, in this case quantum mechanical, like we have to consider that particle as a quantum mechanical particle, and we cannot predict its dynamic or behavior by using simply classical mechanics. So we have to use the laws of quantum mechanics in order to identify its nature, its dynamics. Okay, so that would be the case when lambda thermal will be was greater than or equal to the interparticle distance. Okay, so for this case quantum effects dominant. Okay, like quantum gas or something like that. Okay, now if lambda thermal is smaller than the interparticle distance r, then we can use classical physics to get a good approximation. Okay, so this is basically one of the importance of using of calculating the lambda thermal. Okay, it gives us the scale, the scale of the quantum effect. Okay, so which scale like the quantum effect become important. Okay, so if lambda thermal is greater than the interparticle distance, then the quantum mechanical effect will be much more prominent, and we have to use the quantum mechanics, the Schrodinger equation and all those equations in order to capture its behavior. But if lambda thermal is smaller than the interparticle distance, then you can just use this normal classical physics, that means normal Newton's equations and all, in order to capture its behavior. Okay, so now this is basically all the significance of the thermal wavelength. But here what you have to find out, so so how this lambda thermal is related to the partition function of a system, translational partition function of the system. So let me just write out relationship with partition function. So if z z trans, so if z trans is the translational partition function of a system, of a single particle system which is at a cubic volume v, then z trans would be v by lambda thermal cube. So this is the case when the translational partition function for a single particle in a cubic volume V. Okay, so this is it. Okay, so now these all these things in our hand. Now lambda thermal will be simply lambda thermal will be V by Z trans by 1 by 3. This would be the formula we will be using. Okay, this would be the formula. So what is the problem? In the problem, this partition transfer partition function of each atom, single atom is given, temperature is given, volume is given, then you have to calculate the lambda thermal. Okay. So just substitute all of the things, although we don't need the temperature in this case. Okay, so so this would be the thermal will be simply Z trans is given would be 8 into 10 to the power 33. V is 0.064 meter cube. So just substitute it here. So lambda thermal will be V is 0.064 8 into 10 to the power 33 by 1 by 3. So if you compute this, you will be getting lambda thermal will be equal to 2 into 10 to the power minus 12 meter. Okay, so this would be the final answer you will be getting. Okay, 2 into 10 to the power minus 12. So let me check. So yes, so 2 into 10. So this would 2 into 10 to the minus 12. This would be the correct answer for our system. Okay, so this is problem 1. So now it goes to the problem 2. Okay, so problem 2. So so question number 2 gives paradox in statistical mechanics is related to option A, additive property of the temperature, option B, additive property of the energy, option C, additive property of the momentum, option D, additive property of the entropy. So so this is the four option that's a given. So uh, so before discussing what would be the correct answer, so let me just briefly explain what is the Gibbs paradox is actually. So how does this Gibbs paradox come, right? So Gibbs paradox, we all know, right? Gibbs paradox arises when considering the entropy of mixing for ideal gas, right? So what happens here basically? So in Gibbs paradox, so in Gibbs paradox, uh, if you treat the identical particles as distinguishable, then after mixing, the entropy of mixing, in the entropy of mixing you will get an incorrect result. Why? Because when you mix two identical gas, you would still see, like, when two identical gas are like let's suppose two identical gas, same identical gas is this side and this side of between like there is a clear partition between two identical gas. Now if you remove this partition, when two gases are mixed with each other, it leads to an entropy increase, which shouldn't happen, right? So why you are getting this incorrect result? The reason is that we are considering the identical particle as distinguishable particle, okay? Because in both the cases the two gases are identical, right? But the the entropy that we are calculating after mixing and before mixing is considered by you by using by consider the gas as distinguishable, although they are identical, but still we are considering a distinguishable, and which leads to incorrect result, and that is the reason why Gibbs paradox arises, okay? Now this Gibbs paradox basically, so the Gibbs paradox basically resolved when you recognize these identical particles as indistinguishable particle, right? So this indistinguishability leads to a correction factor in the entropy calculation, and which basically ensures that when you mix those two gases, it will gives you the entropy of mixing will be basically gives you zero value when you like mixes to identical gases, and this should be the result, right? This should be the result you should get, right? So let me just write it one second, okay? So previously, before solving the before get resolve this Gibbs paradox, we are basically treat the identical particle as distinguishable, okay? And because of that we get a incorrect result in entropy of mixing, especially we get an entropy increase when mixing two identical gas, right? Which shouldn't happen, which shouldn't happen. Now so Now this Gibbs paradox, this Gibbs paradox recognize the identical particle. So this Gibbs paradox recognize identical particle are indistinguishable, and this basically leads to a correction. This basically leads to a correction factor in the entropy calculation. Okay, which ensures zero entropy mixing. Okay, so this is the thing. So this is the case. Okay, so that's the reason the Gibbs paradox is very much important. Okay, so now what comes? But in the problem, the question is bit different. So it asks that in Gibbs paradox, statistical mechanics, what are the given below things it's related with. Okay, so uh, uh, so in this case, as we deal with the entropy of the system, so let's first take the entropy and let's try to find out why it's the correct answer. Okay, option D. So option D. So what is entropy? We all know that entropy is basically the extensive property of a system. So the which means that it so it means that it scales with the size of the system. Okay, so that means that let's suppose a system that is composed of small number of subsystems. In that case, the total entropy of the system will be sum of the entropies of the all the subsystems. Okay, so Gibbs paradox basically highlights that this additive property uh, of this additive property, when you consider for entropy, it's this additive property of entropy, we have to consider it much carefully when we deal with the indistinguishable particle, right? So the calculation of entropy without this indistinguishability leads to a non-extensive entropy which violates the expected additive behavior of identical gases, right? So this in this case the paradox to basically demonstrate that the additive property of the entropy is only holds true when the indistinguishability of identical particles is correctly accounted for. Okay, so so the option D will be, so the correct reason will be option D. So the reason is we already know. So this basically holds the additive property of the entropy. Okay, so option D is the correct option here. Okay, so now question number 3. So now problem 3. The molecular partition function for a system in which the energy level are equispaced by E is, so all the options are option A 1 by 1 minus e to the power minus beta e, option B 1 by 1 plus e to the power minus beta e, sorry, the option 1 was plus, this was plus. Option C is 1 by 1 minus e to the power minus beta e. Option D was 1 by 1 plus e to the power plus beta e. So these are the four options given. So you have to calculate the molecular partition function for system in which the energy levels are equispaced by E. Okay, equispaced by E, the molecular partition function you have to calculate. So how you can do that? So now, hmm, so what is a partition function? Basically, um, so in the last lecture we have discussed about partition function is like it's a very important statistical quantity, right? In like let me write it here. So you already know that the partition function is a very is a quantity, is an important quantity which helps to determine many equilibrium property of a thermodynamical system, right? Like if you know the z, which means the partition function of a system, usually we denote it by z. So then you can, from z you can easily calculate for a microcanonical system, you can easily calculate the free energy ln z, or entropy, that is kb ln z, or free energy kbt ln z. So if you note the z, basically you can calculate this internal energy, entropy, free energy, all these things are there which you can calculate for a canonical system. Okay, so now we have to calculate the partition function with a system that is with energy level that is equispaced by E. Okay, so mm, mm. So E means, let's suppose these are the energy levels. Okay, energy. This is the energy. So this is, let's suppose, 0, E, 2E, 3E, and like this, so on. Okay, so let's suppose these are the energy levels, and as you can see, all of this energy level, the spacing between two respective energy levels are E. Okay, E, E, E. These are the separation between the energy levels. Okay, so now for this kind of a system, you have to calculate the partition function. Okay, so we know the like general formula of calculating the partition function, right? Which is z equal to let's suppose there is like let's suppose for a single particle there are n number of energy levels are there, and in that case the it would be, the partition would be like this, right? E to the power minus beta en. The partition function for that for that particle here, it's mentioned it's a molecule. Okay, anyway, for any kind of a single particle, atom or molecule, whatever. So in that case, the partition function, if there is n energy states are there, so in that case this should be the formula of calculating the partition function. Okay, here beta is the 1 by kBt, but here there is no upper limit of energies given, so we can easily consider it that it's maybe a large number of energies there. Okay, so let's suppose that let's suppose energy, that is like, let's suppose the energy is summed over at a very large number, and we can approximate it by using infinite. Okay, so z would be, for our system, n is equal to 0 to infinite e to the power minus beta en. So z is like e to the power beta 0 plus e to the power 2 beta e plus e to the power 3 beta e. Okay, e to the power 4 beta e. So like this, it's gone, right? So now we can write it like this: 1 plus e to the power beta e whole square. You can write it like this, right? E to the power minus beta e whole cube, e to the power plus beta e whole to the power 4 plus now in this problem. So sorry, there is one term I'm missing here. Okay, so between this there will be e to the power beta into 0 plus e to the power minus beta e plus like this. Okay, so z equal to 1 plus e to the power minus beta e plus, so like this. So now okay, so this is it. Now what should we do now? Hmm. uh, Now can you identify, you can like use a property of any geometric series, right? We can use the summation of an infinite geometric series here also, right? For an infinite geometric series, infinite geometric series, we know the formula, right? So if suppose n equal to 0 to infinite up to 1, so in that case the total summation will be 1 by 1 minus r. So this is for a infinite geometry. So let's suppose e to the power minus beta is as r, so we can write it like this, right? 1 minus r plus r square plus r cube, if you consider r equal to e to the power minus beta e plus infinity, right? So you can use this, simply this formula, which gives you 1 by 1 minus r and that is nothing but 1 by 1 minus e to the power beta e. So the partition function will be 1 by 1 minus beta e. Okay. So the correct answer will be option number, which is this option number C, right? Yes, option number C will be the correct answer. Okay. So how would you have done that? Uh, so basically in the problem, it says that you have to find a partition function of molecule for a system in which energy levels are equispaced by E. So what we have done, we have just first draw the energy states of the system. So these are the energy states 0, E, 2, 3. Each of the respective energy state are equispaced, equispaced with a value of E, like how in the question is given. Now this is the general formula of calculating the partition function. Okay, and so energies are 0, E, 2, E, 3. So we have like done the summation. So here we have considered there is like infinite number of states there. Like we have considered the value of the n is like the final value of the summation will be very high, so we can consider it as infinite. So we have taken it like this. So the total partition function is z equal to the power 0 beta e beta minus 2 beta, like this. And then we have used this simplest the summation formula for infinite geometric series. And after substituting this formula, this is the partition function we are getting, z equal to 1 by 1 minus r, which is nothing but this 1 by 1 minus e to the power beta e. And the result is basically matching with option C. Okay, so the problem number 3 is done. Okay, so now comes the problem number, so now comes the problem number 4. Okay, let's first check. So question number 4. The value of molecular partition function for rotation at 3600 Kelvin is given by 19.06. Now to calculate what is the value of the characteristic temperature theta r. Okay, so how do you do that? So in order to basically calculate this rotation partition function, so before that, let me first discuss what is a rotational partition function is. So okay, so the rotational partition function is nothing but it's like the system has some rotational energy states, right? Rotational energy levels, right? So the rotation for partition function basically gives us how in this rotational partition function these molecules are distributed at a given temperature, right? So, and as we all know, this rotational partition function also like plays a very crucial role like to determine like equilibrium thermodynamic properties like heat capacity, entropy and all of that. Okay, so let me just write it. So rotational partition function describes how molecules distribute themselves among rotational energy levels, okay, at a given temperature. So this is the thing. Now so what is the, so let's suppose a rigid diatomic molecule of like a rigid diatomic molecule. You all know for a rigid diatomic atomic molecule, let's say it has like different energy state. Okay, so for if you consider the rotational energy state for a diatomic molecule, the rotational energy state will be like this: Ej is uh, the value of Ej is basically B into J plus 1, where J is the rotational quantum number and Ej is basically the rotational energy of a rigid diatomic molecule. Okay, so if you consider Ej is the rotational energy and B is basically is the rotational constant. Okay, so rotational, this is basically constant value, rotational constant. Okay, so that's it. So the rotational partition function in this case will be all the energy state 0 to infinite 2j plus 1 e to the power beta ej. So this 2j plus 1 factor comes because each rotational energy level can have degeneracy, right? So if for a jth state, a jth state can have 2j plus 1 number of degeneracy. So in order to consider that, we have to multiply this partition actual this e to the power beta ej to the with the 2j plus 1 factor. Okay, this basically accounts for the accounts for degeneracy of each rotational level. Okay, this is the basically the expression of j rotational. Okay, now for our problem it's basically a bit simplified. Okay, so as you can see, for our system the temperature scale is very high. As you can see, it is for around 300 Kelvin, which is too high. Okay, 300 or 3600, sorry, it was actually 3600, sorry, it was 3600. Okay, so for 3600 the temperature is very high, so we have to approximate this expression. Okay, so what we have to done, so when temperature is very high, so that means kBT is far greater than this rotational constant beta, then this whole sum we can approximate by an integral. Okay, so in that case the sum can be approximated by z rotational equal to t by theta r. So what is theta r? Theta r is basically is known as the characteristics temperature. Okay, that we have actually asked to find out. So theta r is the characteristic rotational temperature. Okay, so this we have to basically find out. Okay, so this formula is basically very much useful. Okay, to for high temperature to like quickly calculate the partition function or like characteristic temperature, whatever. So if characteristic temperature is given, we can quickly calculate the rotational partition function in the case where the kBT is much greater than the b value. Okay, and another expression, the theta basically is equal to b by kb. B is this rotational constant. Okay, so let's just calculate. So T is already know, T is 3600 Kelvin and Z rod value is what is 19.06. Now theta will be 3600 yes 30, sorry, no, so theta will be, yes, so theta will be T by Z rod, right? So 3600 by 19.06. so let me calculate what is the value. So it's almost close to 18.87. Okay, so okay, I have not written the options there, so anyway 18.87. okay, so these was the option. So let me also write the options. Also forgot to write the options. Okay, 1 second. These are the options. Option A was 18.88, option B was 94.44, option C was 196.92, 196.92, option D was 96.96 Kelvin. So these are the 4 options are given, and the correct option would be then option option A, right? So 188.88. This is the correct option. Okay, so question number 4 is done. So with this we have completed all the assignment for this tutorial 6. Okay, so we don't right now we don't have any new assignments related to this week. So what do? We have still 1 hour remaining for our class to finish. So what I do, I would discuss some of the problems from like previous tutorial. Okay, so like I'll be discussing mostly from tutorial 3. Okay, like for this week, for this course. Okay, for like this year's course, I will discuss some of the problems from tutorial 3. Okay, so let me do this. So tutorial 3. Okay, tutorial 3. So tutorial 3, question 1. So question 1 is the vapor pressure of a solid selenium is given by log P mm equal to 12.78. Okay, this is for solid selenium. This is the expression of the vapor pressure. Okay, and of liquid selenium, the log P is given equal to minus 5390 by T plus 8.63. Then you have to ask to find out the triple point, this is in degree centigrade, so triple point, this is basically a temperature. Okay, temperature, triple point temperature of selenium is option A 267.33, option B 347.67, option C 493.98, option D 220.98. Okay, so these are the four options given. So you have to find out what is the triple, based on this information, what is the triple point, okay, of the selenium. So before solving this problem, so let's just briefly discuss what is a triple point is. So in thermodynamics, triple point is a very specific conditions. Okay, so it's basically a temperature and a pressure at which the three phases of substance, solid, liquid, gas, coexist in a in a thermodynamic equilibrium. Okay, so let me write it. So it's the temperature and pressure. For our case, we have to only calculate the temperature part. Okay, because it's actually dependent with the pressure actually. Okay, so it's the temperature and pressure at which the three phases of a substance, solid, liquid and gas can coexist in thermodynamic equilibrium. Okay, so that temperature and this temperature that we have to find out. Okay, so let me also, one second. So let me also gives you a diagram. In this way will be so this is a schematic diagram. Okay, so this, suppose this axis there is pressure and this axis there is temperature, T with P. So this is basically the triple point. Okay, let me mark in red. Okay, triple point. And so here it consider the solid phase, here is the liquid phase, and here comes the vapor phase, vapor. So this is the point where all of this is basically schematic diagram. So these are the phase separation lines. Okay, and you can see this triple point is important because at this particular pressure and temperature, all these three states basically coexist with each other, okay, in a thermodynamic equilibrium. So that's why this is called a triple phase, triple point. Okay, so now in our problem we have to find out a particular pressure, particular temperature where both this solid and liquid form of the selenium coexist with each other. Okay, so as you know, at triple point of selenium, the pressure and temperature of solid and liquid phase will be same, right? Because these two phases basically coexist, right? So their pressure and temperature should be same at this triple point, right? Will same. So therefore Therefore we can just equate the pressure expression for solid state. This is the pressure expression for solid state, this is the pressure expression for the liquid state. We just have to equate these two. Okay, so this basically gives, therefore we have log P of solid equal to log P of liquid. So this basically gives minus 7440 by T plus 12.78 equates to minus 5390 by T plus 8.63. This basically gives you 7440 by T minus 5390 by T equal to 12.78 minus 8.63. So now if you subtract these two, basically gives you 2050 equals to 4.15. Okay, now T is here 2050 by 4.15, and temperature would be, if you divide 2050 with 4.15, it gives you 493.97 Kelvin. So this is the temperature, this should be the temperature at critical case. Okay, critical point. So now now the thing is so now in the question you have to find out it's in degree centigrade, right? So yeah, it's in degree centigrade. So in degree centigrade, so it would be have to minus it to equal to in degree centigrade you have to subtract it with 273, which basically gives you 220.97 degree centigrade. So yes, so that would be the correct answer. Okay, so option number C would be the correct option. Okay, so this is it, option number C. So so you have understood, right, how to do this problem. So basically you have to equate the like in triple point, like both phases like solid, liquid and gas phase coexist with each other. So for this problem you have to equate the vapor pressure of both solid and liquid phase with each other in order to get that particular triple point, because in triple point both the pressure and both the pressure should be same. So in this case for the selenium the pressure expression is given, the vapor pressure. So to solve this problem we have to equate these two pressure with each other, solid and liquid case, and we equate it and solve the equation for the temperature, and this is the results we have got, and T is basically 220.97 degrees centigrade. Okay, so the question number 1 is done. Now let's jump to the question number 2. The fugacity of NH3 gas, which constant B is given 3.707 into 10 to the power minus 2 liter per mole inverse at 25 degrees centigrade, having true pressure of 10 atm is option A 10.153, option B 11.00, option C 15.67, option D 9.87. Okay, so these are the four options that are given. Okay, so fugacity thing. Okay, so in the previous tutorial also we have discussed about the fugacity. Okay, so let me just explain it here once again. So answer. So what does basically fugacity coefficient is? Okay, so basically you all know that uh, for ideal gas, whenever we are when we are considering ideal gas, we not consider like the pressure, the individual volume of each molecule, and also we are not considering like the individual momentum of each particle. Okay, but if you consider those two things, then the pressure term would be different, right? The normal pressure that we are using for ideal gas would be different, right, if you consider those two correction terms are there. Okay, so fugacity basically is this basically the correction factor that accounts for that for deviation from the ideal gas behavior. So let me just write it. So the one second. So we don't know the ideal gas is a simplified simplified model for gas behavior, right? But real gases deviates from this ideal gas behavior, right? So to now by considering these two facts, fugacity you can call fugacity is an you can call it as effective pressure. Okay, effective pressure. So effective pressure, effective. So why we are saying it effective? Effective in the sense that the pressure of real gas, not ideal gas, so pressure of a real gas, that means by considering the non-ideal behavior. Okay, so this is basically the definition of fugacity. Okay, now for our problem, so this fugacity coefficient. Okay, so what is a fugacity coefficient? So this fugacity coefficient which is here termed as phi is a correction factor. Okay, correction factor that accounts for deviation from ideal gas. Okay, so this is that means it's basically a ratio of gas fugacity. Gas fugacity means that effective pressure. Okay, these are two different, fugacity coefficient and normal fugacity. Okay, so fugacity to its ideal pressure. So phi is equal to F by P. So phi is the fugacity coefficient, F is the fugacity, and P is the pressure. Okay, so this is it. Okay, so now in the problem, now there is for a van der Waals gas. Okay, there is another expression of fugacity which is this for fugacity coefficient. So we actually need this thing also. Okay, so phi is e to the power beta P by RT. Okay, B is that in the van der Waals gas equation, you know, there is a volume correction term is right there. So B is that volume correction term. Okay, P is the pressure, and so everything. So so it's so P is the true pressure and T is the temperature. So these are the options. These options are given. Okay, so with these all this information, you have to calculate the fugacity coefficient. Okay, so now in the problem, this BPR, this BPRT, every value is given, right? So P value is given here 3.707 10 to the power minus 2. 3.707 into 10 to the power minus 2 liter by mole inverse. So liter mole inverse. P is given. P is the true pressure, right? True pressure is given 10 atm. So P is 10 atm. R, you know, ideal gas constant. You can use it in joule format. So 0.0821. Oh, sorry, at liter atmosphere format. And temperature is 25 degree. 25 means 273 plus 25 is 298 Kelvin. So phi is e to the power 3.707 10 to the power minus 2. P is 10 atm. R is 0.10821 into 298. So if you do all this calculation, you will be getting phi as 1.015. Okay, this would be the fugacity coefficient. Now in the problem, You have to find a fugacity, that means the effective pressure. Okay, so if you get the fugacity coefficient value, from there you can easily calculate, right? So phi is equal to, F by P. So F should be equal to phi into P, so that means F equal to 1.015 into 10, so that gives me 10.15 atm. Okay, so this would be the value of the fugacity. Okay, so this would be the result. So correct result will be this one. So this one. Okay, so problem 2, option A is the correct option. Okay, second. So problem 3. Now so problem 3, the latent heat of fusion of deuterium at 18.56 is 47 calorie per mole inverse. Okay, the slope dp dt is 40.5 kg centimeter square inverse mole inverse. The difference between molar volume of solid and liquid, solid and liquid deuterium at this temperature is, basically you have to calculate. Okay, so option A is 0.0625, option B is 0.0626, option C is 2.669, option D is 0.261. So, and one information is provided, is 1 calorie equal to 4.184 joule and G is 9.8 meters square. Okay, So for this problem, what is the thing that you have to use? So you have to basically use the Clausius-Clapeyron's equation, right, in order to solve this problem. So what is basically a Clausius-Clapeyron's equation? So let me just write. So the Clausius-Clapeyron equation describes the relationship between the temperature and pressure of a substance during the phase transition. Okay, so let's suppose liquid is transforming to gas. So in that case, the normal temperature that is required to get liquid to a gas is 100 degree, right? uh, for liquid, sorry, so for liquid, sorry, so liquid to gas, so it's for water, it's 100 degrees centigrade, right? All of you know this, the temperature, but that temperature is only valid at STP, that means standard temperature and pressure. Okay, so that is valid only at a certain pressure, right? If you change that pressure, this temperature required for phase transition will also get changed, right? So how to build a relationship between this changing pressure, how basically this effect into the change in this transition temperature, we basically need a relationship between these two, right? So in order to get that, the Clausius and Clapeyron's made this equation called Clausius-Clapeyron's equation, and the equation is basically dp dt equal to L T into del V. So this is like, if you change this temperature, pressure, this critical pressure means the pressure that is required for phase transition by a small amount dp, then what will be the change in the temperature, okay, at which this phase transition occurs. What would be that change? That change will be, let's consider as dt. So how this dp and dt are related to each other, we can do this by using this simply Clausius-Clapeyron's equation. Okay, so basically here, dp by dt gives you the rate of change of pressure with temperature. L is the latent heat, T is the absolute temperature, and delta V is the change in volume during phase transition. Okay, phase transition. So these are all the things are given, dpdt. So now in the problem, Mm. Mm. So slope is given, dPdt is given, but we have to change the units. Okay, latent heat is given, the difference between molar volume is given. uh, Molar volume. Oh, so the difference in the molar volume we have to calculate. Okay, so now let's write it. Okay, so one by one. So T is given. T is nothing but 18.56 Kelvin, right? 18.56 Kelvin. Delta is, that is latent heat, is 47 calorie per mole inverse. I think this is correct. 50.5, huh? 47, yes. And dPdt is 40.5 kg centimeter square into mole inverse. Okay, but this is like given in terms of mass per area, right? But in our case we have to convert it into the suitable unit so that we can use this value. Okay, so how can you do that? We have to simply dPdt. So I have to convert all the units. Centimeter square have to convert in meter square. Meter, that then it should be a second inverse would become, because we have to convert it into the suitable pressure unit. Okay, this is normal just mass per area, but that is not sufficient, right? Because all the units should be in correct order. So dPdt, you can multiply it 40.5 into 9.8 into 10 to the power minus 2, 10 to the power 2, sorry. So in this way it would become kg meter into second square. Okay, so in order to like change the units from this mass per area to a pressure unit, we have multiplied with the gravitational force constant, right? And centimeter we have converted into meter, so that's why the 10 to the power plus 2 factor had come. Okay, and rest is same, mole inverse, Kelvin inverse. There should be a Kelvin inverse here also. Okay, so that's it. Now this is it. So now, 1 second, slope. So now you have to calculate what is the del V. Okay, so del V is basically, this is basically L, sorry, this is L, latent heat. So del V is basically L by T into dP dt, right? So here, actually L is given in calorie. Okay, so we have to convert it into joule, and 1 calorie is how much joule is already given in the problem. Okay, so what we can do, delta V we can use, L is 47 into 4.184 by 18.56 into 40.5 into 9.8 into 10 to the power 4, which basically gives you 47 into 4.184 by 18.56 into 40.5 into 9.8 into 10 to the power 4. Okay, so all this, so there is this, so units are cut out. Then so if you do this multiplication, this would simply gives you this whole things cancel, and this will gives you delta V equal to 2.669 centimeter cube mole inverse. So there are many units are there actually: kg, meter square, second square, mole inverse, kg, meter inverse, second inverse, mole inverse, and Kelvin inverse. So all of these units cancels with each other, and you will survive with this centimeters cube mole inverse. Okay. So this would be the final value you'll be getting delta V. Okay. So let's just check, is there 2.669? Yeah, there is 2.669, right? This would be the correct answer for this problem. Yeah. So 2.3 is done. Problem number 3 is done. Now we goes to the problem number 4. Okay. So problem number 4 is which of the following term is not zero when ideal two gases are mixed together. When ideal two gases are mixed with each other. Option is delta H mix. Option B is delta V mix. Option C is delta G mix. Option D is delta U mix. Okay. Hmm. So in the problem you can see this, you are considering ideal gas. Okay, so when you are considering the ideal gas, this means we have approximated that there will be no interaction among the particles inside the gas, right? That is one of the approximation in the ideal gas. Okay, so as it's sorry as it's an ideal gas, as there are no interactions between the gases that are mixing, right? So uh, so that means both this delta H mix, that means the that is enthalpy, or delta V mix, volume is obviously not going to change, as and also the delta U mix, that is the change in internal energy, both these three terms will become to zero, right? That's there are basically no interactions, okay. But when you consider the Gibbs free energy, as you know, when you mix like this, suppose two gases are there, it's just separated by this enclosure. Now if you remove this enclosure, these two gases mixes. Now in this case we already know that there is a change in entropy, right? So which basically known as the entropy of mixing, right? So because of this change in entropy, there should be change in the Gibbs free energy as well, okay. So that means the change in Gibbs free energy will be not simply not equal to zero. So let me write it. When you mix two gases, there will be entropy of mixing, which basically confirms that there should be a change in the Gibbs free energy, because Gibbs free energy itself depends on the entropy, right? So delta G mix would simply not equal to zero, okay. So this is question number 4 is done. Now we move to the question number 5. So what question number 5 says, okay, so question number 5, standard chemical potential of oxygen at 300 Kelvin is 10 kilocalorie per mole inverse, okay. The volume decreased to 2.46 liter isothermally, and the increase in free energy is found to be 1.342 kilocalorie. The fugacity of oxygen is what? That you have to find out, okay. So let me write the correct option. Let me write the possible options. So 9.5, option B is 1.0, option C is 5.46, option D is 7.87. Okay. So these are the options that are given. So now we have to calculate. Okay, so how to do that? So in the previous problem I've already discussed about this concept of fugacity, right? Now this fugacity actually related with the chemical potential by a formula, okay, by relation, certain relation, okay. So you have to basically, because the chemical potential is in the problem, the chemical potential value of the oxygen is given at a certain temperature. So basically you have to use that particular formula in order to calculate the free energy and all these things, okay. So in the end you have to basically calculate the so free energy and all the chemical potential is already given. So basically from there you have to calculate the fugacity, okay. So now how to do that? So hmm, for any real gas, the chemical potential is related to fugacity as mu equal to mu naught plus RT ln F by F naught, okay. Now here mu is the chemical potential, right, at F, and mu naught is the chemical potential at F naught, okay. R is the real gas constant, T is the temperature, and F naught is basically the one is the reference fugacity, okay. Reference fugacity. Here in this problem, the reference fugacity is it's not given actually. So anyway, it's not needed. You have to basically calculate. Mm. Now for actually this reference fugacity F naught value in standard problems considered as 1 bar actually. Okay, so we can take it as 1 bar. Okay. So now the whole formula reduced to delta mu minus mu naught basically. So mu minus mu naught is RT ln F, and mu minus mu naught, that is change in the chemical potential. You can consider is this change in chemical potential equal to change in the gives free energy. Delta G is RT ln F. Okay, so this formula we are going to use for this problem, because in the problem itself, as you can see in the problem, the temperature is given. Temperature is 300 Kelvin, right? So temperature is given. Temperature is 300 Kelvin. Standard chemical potential is also given at that particular temperature, right? So that standard chemical potential would be, what is the value, is 10 kilocalorie per mole. Okay, so mu naught is simply 10 kilocalorie per mole. Second thing is volume decrease. So volume decrease 2.46. Okay, so this for this problem, the volume decrease, that means decrease to V1 to V2, and V2 value is 2.46. Okay, but that value I don't think it's required to in order to solve this problem, but anyway. And the increase in free energy, that is delta G. Increase means delta G value will be positive, simply 1.342 kilocalorie. Okay, so these much informations are given already in the problem. So now you have to calculate the f. So f is basically e to the power delta g by rt, right? So this is coming from here. So if you just put delta g by rt this side, and put the ln like e to the power, like ln has e base, so if you put e this side, so e to the become e to the power, so f simply becomes f equal to e to the power delta g by rt. So now f would become e to the power delta g 1.342 into 10 to the power 3 by 1.987 into 300 by, it simply gives you 9.518 f. So this fugacity value would simply give you 9.518 for oxygen. So question number 5 is done. Now the last question is question 6. So question 6, in the absence of any phase transition, the change in entropy when a system is heated from T1 Kelvin to T2 Kelvin at constant pressure is given as, there are the four options: delta G1 minus delta H1 by T1 minus delta G2 minus delta H2 by T2. Option B was Cp ln T2 by T1. Option C was Cp T2 minus T1 by T2 T1, and option D is mu1 T1 minus mu2 T2. So these are the four options that are given. So now let us calculate. Okay, so answer. So here is so the main thing is basically what happens here. You heated a system, and because of that, it temperature rises to T1 degree, T1 Kelvin to T2 Kelvin. And because of this temperature change, let's assume that there is no phase change is happening, right? This is one important approximation that here they have considered. And by taking in all of this thing, you have to calculate. So by taking into account all of this thing, you have to basically calculate what is the change in entropy. Okay, so how to do this is very straightforward. Okay, so we already know, right, this thing. So from first first law we already knew all these things, right? Dq equal to du plus dw. So dq already know, tds equal to du is cp dt plus pdv. So ds basically cp dt by t plus p dv by t. Now ds cp dt by t. Now here we know from Charles' law PV equal to KT, right? So we can write P by T as K by V. So we can write it like this, K by V into dV. Now if we do simply the integration both sides, which simply gives you ds equal to delta S n. Okay, one thing is I forgot to consider here is n. Okay, because n is the number of moles, right? So n is cp ln, sorry, cp ln if it's t1 to t2 and v1 to v2. So so delta s should simply become n cp ln t2 by t1 minus n oh sorry, this should be r. So pv equal to nrt, right? So this should be nr. Okay, so nr. So nr ln okay, ln v2 by v1. Okay, but what you can do here, we already know v2 by v1, sorry, p1 v1 equal to p2 v2. So p1 by p2 equal to v2 by v1. Okay, so we can write it like delta S n cp ln t2 by t1 minus nr ln, sorry, this should be plus ln plus p1 by p2. But here there is no phase change is happening, right? So there is no like volume change and nothing is happening. So p1, like this whole thing is at constant pressure, right? In the problem it's mentioned, right? It's in constant pressure. So p1 or p2 are basically the same. Okay, so p1 is basically equal to p2. So ln1 gives you basically 0. So delta S n cp ln t2 by t1. This simply would be the change in the entropy, and for 1 mole n should become 1, right? N equal to 1 for 1 mole. So the correct option would be option B. Okay, so with this we have completed all of the problems, and so right now I hope all of you understood all of the problem that I've solved. So with this, let me end the session. Okay, thank you.